Okay, so for this last set of slides, we're going to talk about deep recurrent Q networks. The idea is that we've now been talking about partial observability, and I need to tell you describe at least one method in practice that would make use of that. And then, so I introduce essentially the basic concepts where traditionally we could express partial observability through hidden Markov models and then do some planning with partially observable Markov decision processes. Now in reinforcement learning, with deep reinforcement learning, it turns out that we often replace the hidden Markov model with a recurrent neural network. And then we're going to see now if we combine a recurrent neural network with a deep Q network, then it will lead to some interesting technique, and that's the subject for today. Okay, so I will introduce then recurrent neural networks. This will be a very brief introduction. In particular, we'll talk as well about one type of recurrent neural network known as long short-term memory networks, or LSTM networks, and then we'll see how they can be used inside deep recurrent Q networks. Okay, so again, as a quick recap, so when it comes to partial observability, from a theoretical perspective, one way of thinking about this and modeling the partial observability is through a hidden Markov model. Right? So our hidden Markov model has these parameters, and then graphically it looks like this. And then the key is that we can use that to compute a belief at every time step, which is essentially a distribution over the current state given the observations up until now. Right? So this is a very useful tool to allow us to gather all the information in the previous observation to tell us, or at least to refine some belief about the current state, because if we knew the current state, then we could simply condition our actions on that current state, but failing that, we're going to condition actions on the belief. Okay, so that's what we've discussed. Now, it turns out that we don't have to use HMMs per se to compute beliefs. So with deep reinforcement learning, and what is now possible as well is to use a recurrent neural network to do the same. So here, a recurrent neural network is really a neural network where the outputs can be fed back to the network inputs, which creates a recurrent structure. So here, I've got a very simple recurrent neural network where I've got my input X, and then it goes into some computational unit H, and then H perhaps could just be the output. But now I don't have to just produce an output on the spot. What I could do is simply take that output and feed it back to H, and then continue computing, right? And then I could do this over and over and over and over, and then this will have some very interesting properties. In particular, if I've got a sequence of observations, the idea is that then I could process these observations one at a time and always kind of just perform the same computation with that, which will lead to a recurrent neural network. Now, the easiest way of understanding recurrent neural networks is to unroll the recurrence. Okay? Because when you look at this, this is still simple, and then this black square indicates that this is a link that essentially takes the output, feeds it back as input, so it's a link across time steps. But now if we want to see what happens when we unroll the computation over several time steps, then it would give us a network that looks like this. So here, with this network, you see, we could imagine that we start with some state, and then at each time step, we have a new input that is fed in and combined with the previous hidden state, and then we can compute a new hidden state. Right? So then we would just feed those one at a time, and then it's natural to see that, oh, this type of neural network perhaps can be thought, or otherwise could be used as a form of hidden Markov model. So in fact, we can argue that recurrent neural networks here can be used to simulate and even generalize hidden Markov models. right? So a hidden Markov model, if I just go back, right, it has a similar structure, right? So I've got my hidden states here, and then I've got the observations below. And the idea is that at every time step, I'm going to combine one new observation with my hidden state through this update here. But now this is a very specific way of doing the updates. And then perhaps we could do the updates in different ways. And then the recurrent neural network is going to allow us to generalize this. So here the idea is that I've got a function f that will take as input x and the previous hidden state, and then we'll combine them together. Here it will be combined through perhaps some type of linear combination with a nonlinear activation function, and then produce a new representation, a new hidden state. And then it can be even more complex than that. So I mean, F in principle could be an entire neural network with several layers that perform lots of operations to process X and also to process H, right? So in that sense, it can be quite general. But in any case, we can also set up F to correspond precisely to the equation that we have here. So if we want, we can use a recurrent neural network to define or to correspond exactly to a hidden Markov model. But the beauty is that we are not restricted to that. We can essentially define F in any way we want, and then it will lead to some type of process whereby we can simply feed in one input at a time and compute a new output. Any questions regarding this? Okay, good. So, all right, so now based on this, the next question is going to be now, how do we obtain that recurrent neural network, right? So in the same way as for the HMM, we talk about how if we have data, we'd like to be able to estimate the parameters of the HMM. Now here, if we have data, we'd like to estimate the parameters of the recurrent neural network. And the parameters are really just the weights that would define this function f. So normally you say I combine x and h, and then their inputs to the function f that outputs h at the next step. Now here, typically in neural networks, our parameters are weights, right? So we need to have a way of estimating those weights. So to do the training, it turns out that we can do backpropagation on the unrolled network, because again, if I look at this network, right, so even though I said that, well, this is a recurrent neural network, from that perspective, once it's unrolled, it actually looks like just a regular feed-forward neural network. In fact, a deep feed-forward neural network that has a layer that's the input here, right, and then several other layers, and then there's the output here, right? So you can always think of the unrolled network as a regular feed-forward neural network. So from that perspective now, it's easy because we know how to train regular feed-forward neural network. We can do backpropagation. We can simply do compute the gradient automatically and then take some steps in the direction of the gradient. So we're going to do the same thing here. The only difference is that you see we have the same function f applied, which means that we're going to have weights that are the same at each stage. So the weights are going to be shared. Normally in a feed-forward neural network, you would have different weights associated with different edges, and then there's no sharing of the weights. But from a mathematical perspective, it's not a big deal. It just means that we have a function where the weights that happen to be the variables will be repeated in different places in our function, right? But then we can still compute the gradient with respect to those parameters. So with respect to the weights, even if they appear in many places, right? So it's just going to be gradient descent as usual. Okay, so in the neural net literature, though, they would call that backpropagation through time, because you're unrolling the neural network and then you're doing backpropagation through time, but really it's just backpropagation. Okay, so then there's nothing special about it. Okay, now actually there is something special about it, which is that it's actually more challenging to optimize recurrent neural network. So here, the gradient vanishing problem will typically be more important, and you can also have gradient explosion. and then it's difficult to have some long-range memory, and then there might also be some prediction drift. So there's, for anyone who's got experience with recurrent neural network, they are typically much more difficult to optimize, and these are some of the issues here. So the first one for gradient vanishing, why it's even more important, is simply because when you unroll your network, you're effectively creating a deep neural network, and then the depth of the network has to do with the number of steps that you unroll for. So if you unroll for many steps, right, you will be creating a very deep network, and then as a result, this will amplify the gradient vanishing problem. Okay, and maybe the other aspect is that because we have the same weights that appear at every stage, then there's some type of composition of those functions that occurs, and then it makes as well the overall function perhaps much more nonlinear, and there's a lot more opportunities to have local optima, and then so as a result, it also tends to be difficult to obtain good results. So you often have to try different hyperparameters and then maybe different starting points and so on to obtain good results. Okay. All right, so one way of mitigating those challenges is to use the long short-term memory, which is known as the LST M Unit. So the idea is that here we have a group of cells that we're going to combine together. So it's going to be an aggregated unit. And then all of this would essentially replace one node. So at every step, you know, the hidden node, instead of just taking a linear combination followed by a nonlinear activation, right, then we could do something that is a little more complex. So I said that f can be an arbitrary function, and in particular, it could correspond to computing this. Okay. So this type of structure is interesting because it tends to help to remember information over a longer period of time, and also helps to mitigate the gradient vanishing problem. Okay. I'm not going to go into the details of why that is for gradient vanishing, but let me explain a bit more for the memory part. So it's not obvious when you look at this drawing. So this is a drawing for the recurrent form, but now let's unroll this type of unit. So if we unroll it, the easiest way to think about it is just to start from a regular recurrent neural network where perhaps I have some inputs here. They feed into some hidden units, and then the hidden units are going to produce some outputs. Now, this LSTM cell has, what's special about it is that it has some gates. So here I've got a hidden unit, but then the information that would normally be fed to the hidden unit, which is the input, and then also the previous hidden unit, these are going to be modulated via some gates. So that's why I've got some multiplications here that are going to decide whether the information should be passed on to the hidden unit or not. So concretely, what will happen here is that I will introduce some gates on my network where, so for all the inputs, I'm going to have a gate. The gate is going to compute a probability that's essentially a number between 0 and 1, and then it will multiply with the inputs here. So if I have a gate that is equal to 0, and then I multiply, it will essentially nullify the information from the input. So then here there will just be a 0 going in, and then this will have no impact. If on the other hand the gate is open and is equal to 1, then when I multiply by 1, it means that the input can go through, and then it will be used to impact the hidden unit. So this is for the inputs, but then we also have a gate that will determine what happens with respect to the previous hidden unit. So sometimes what we might want to do is forget what we have already stored into that hidden unit. And then so the gate equal to 0 will essentially nullify what we had before. And then it means that we're forgetting the information. If the gate here is equal to 1, then we remember the information and then it's passed along. And then same thing for the output. We're going to have a gate. And then the gate will determine what goes out. So here it's a little bit weird, but still the gate will essentially either nullify the information or allow it to be outputted. Okay, so same concept. Now all of those gates, they need to have some information. So what they do is they each compute a number between 0 and 1 that you can interpret as a probability, right? And then that will keep the gate open or not. But then what information goes in? Here we would simply use the input itself as well as the previous hidden unit. Okay, so all these additional arcs essentially show that this is what I had before, and now for instance if I want to know what goes into this input gate, it will be this input unit as well as this hidden unit. So that's why I have now two arcs, two green arcs that go in. Okay, and then same thing for the forget gate. I'm going to have this input as well as the previous hidden unit, and same thing for the output. I'm going to have the previous input and the hidden unit. Okay, so this is the scheme at every step, and the idea is that then these gates are going to compute numbers between 0 and 1 that will determine what information is allowed to keep on flowing throughout the network, and that allows to regulate better. For instance, if I would like to remember something from the beginning, then perhaps I would like to have my forget gate set to 1 so that the information flows all the way through. And then if I don't want to modify that, then I want to make sure that the input gate here is going to be set to 0 so that it doesn't affect what we are passing through. Right? So this is the idea that now we have a mechanism through those gates to explicitly control how the information will be remembered and transferred at each time step. So now there's a better chance that some information earlier into the process can make it all the way to the end if the gates are set properly. Whereas before, when we just had a regular recurrent neural network, in fact, yeah, if we just have this, the idea is that now we're going to compute H1 from H0 and the input, and then at every step you see the input is going to impact H1 and perhaps modify whatever we had before. And then if the network is not well tuned, then it might in fact just override the information that we had before. So typically what would have happened is that this information would gradually be overwritten to the point where it's just lost, right? So if you want to remember information for a longer period of time, then those gates can be used to help in terms of preventing this loss of information. Okay, any questions regarding LST M units?
So is there a gate value computed for each unit?
Yes, so here you see I've got gates. Essentially the gates are with respect to every edge, right? So with respect to the information, so here for this hidden unit normally it takes as input both the previous hidden unit and the input, but now we've got gates that will decide what information goes in here. And then this is the case at every time step.
But why the inputs will be involved in the forget gate?
Well, so okay, for all the gates, right, we need something to allow them to determine whether it should be 0 or 1 or some number in between. And now what is the information that we have available at that stage? It's really just the previous hidden unit and then a new input. Okay, so here you might say, well, since it's using the same information, right, as what H3 would use, isn't that redundant? Okay, so from a pure information theoretic perspective, it is indeed redundant, but from a computational perspective, it is often something that works better. And here, one hypothesis is simply that when we do the optimization, it might just help the algorithms like gradient descent to find good parameters, simply to just, I guess, modulate the gates, and then those gates then will modulate what information goes in. So decomposing this in like 2 steps like that might just be easier for the algorithm to optimize. Because otherwise, yeah, here you see we have both the input and H2 that goes into that forget gate that impacts this. Same thing for this input gate, but then the original recurrent neural network anyway had just H2 and input 3 that just went in here. It's just that we're organizing the computation differently. Yeah.
The gates are either open or closed, or they can be, for example, half open. And what is half open mean here?
Right, so yeah, here they can be half open. So in fact, yeah, the easiest way to think about this is that it's going to be open or not, but in practice, we typically represent the gates by a sigmoid unit, okay, and the sigmoid unit will produce a number between 0 and 1. So if it is 0.5, then it would be half open, and then this would mean that we have like half of the information from H2, like we would take that vector and essentially multiply it by 0.5, so it would be half of its magnitude, and then it would be fed in still, okay? Yeah. Okay. All right, so we're almost done, but let me now briefly introduce how we can use those recurrent neural networks in a Q network. So, okay, we've talked about Q learning with convolutional neural networks, let's say to play Atari games. So typically, we would have just some neural network to compute the Q values. But now what we can do is have, let's say, in the context of video games like Atari games, we would have images here. We would feed this through a convolutional neural network. This would then be fed into an LSTM network. So here, this layer is essentially this network here. Okay, so it's just a little too complex to fit on this slide, right? But then this layer would correspond to this entire network, and then this particular bar here is a hidden unit, right? So it's a hidden vector. But the idea is that we would then have a convolutional neural network that corresponds to our observation model. So it will extract information from the image, and then it will produce some hidden representation that captures presumably whatever is relevant in the image. Now that information will be combined one time step at a time. So we've got an LSTM network here that accumulates the information from all the images. So the idea is that, let's say you play a video game, and then images are not a state representation, but maybe just an observation of whatever is the underlying state of the game. Then you can accumulate information from all those images and obtain overall perhaps a better approximation of the state. And then, so what is computed with the LSTM network can be interpreted, so here those hidden vectors, you can interpret them as really being beliefs. The beliefs, in theory, should be distributions with respect to states. Now here, let's think of these as really just vectors of numbers. They're not going to correspond necessarily to distributions, but those vectors of numbers, you can think of them as maybe a sufficient statistic of the information, right? And that's what beliefs are. They were really just sufficient statistics. They happen to be distributions, but perhaps we can have sufficient statistics that are not distribution necessarily. And that's what the LSTM network does. So it computes some sufficient statistic, and then it propagates that over time. So yeah, so that would be one representation for doing this. And now, if we plug this into the Q-learning algorithm, so this is the same as before. The main difference is that now we cannot just have some short samples, but we need to work with entire episodes, because the LSTM network will take one image at a time and accumulate information, and then we need this as part of the algorithm. So we would have an episode, and then we would simply sample from, so I guess we're going to store information in terms of episode as opposed to just triples of a state and action and then the next state. So here we store the entire sequence, and then we would use this, where here I've modified the algorithm to reflect the fact that there's a recurrent neural network. Right? So here there's the Q network that takes as input the recurrent neural network. So if I just go back, you see this is my recurrent neural network, and then from this there's going to be another network that computes the Q values. So that's as before. So this is our Q value network, and then so it sits on top. So here in the algorithm, you see the Q network takes as input whatever comes out of the recurrent neural network at each step. And then so they would have some weights, and then that gets updated in the usual way. Okay, so so this is the approach. This is the naive way of implementing this. There's a more efficient way of doing this that I explained in this slide, but in the interest of time, let's just go straight to the results. So if you do this with Atari games, it turns out that Atari games, the images are good approximation of the state, so it won't make a big difference, but at least for some games it does make a difference. So here this is the deep recurrent Q network versus a regular deep Q network, and then we can see that there are two games here, Double Dunk and Frostbite, where the results are much better. Now this was on the original games, but now if we introduce some flickering of the images, where perhaps every once in a while some frames are skipped and therefore we're missing information, then it becomes important to use a recurrent network. So we can see that as the percentage of frames that remain gets lower, then there's some loss of information, but the recurrent Q network tends to obtain higher values than just a regular deep Q network that ignores that problem. Okay, so in general, this shows that if you have partial observability, here they're creating the partial observability in an artificial way, but this is just to illustrate the concepts, then you can obtain much better results. Okay, all right, and this concludes the slide, so I'm going to stop here. And then again, next class, we're going to have 2 presentations, and then this will be the new mode until the end of the term.